Good morning, everyone. We thank you for participating in today's webinar. Quick reminder, the 4C conference is August 18th to the 20th in Austin, Texas at the Hilton downtown. Today's webinar is featuring Montrose Environmental and Stephen Yax. We'll be talking about emerging technologies for sampling and quantification of HRVOC, ethylene oxide, and then fence line and ambient monitoring and monitoring of emission sources. And with that, Stephen Yax, I will let you take it away.
Thanks everyone for stopping by. We're going to talk a little bit today about some of the emerging technology work that we've been working on, and we're going to focus a little bit on HRVOC, OHAP, regular HAP, and of course ethylene oxide that everyone loves. And we're going to look at a little bit of fence line, ambient, and some stationary emission sources as well. So real quick on this one, this kind of details it a little bit more. There are multiple technologies available to do a wide variety of these field analysis. So we'll look at some methods specific for the ethylene oxide and the OHAPs. We'll start out with a little bit of sensor work and how we deploy those, a little bit of optically enhanced FTIR for OHAP analysis, and then we'll look at the proton transfer time of flight mass spectrometry for a wide range of these applications and analytes. So I'm going to start off, and we'll go from maybe the little ease of use down to a little bit more complicated systems. So we'll start with some of the dedicated sensors that we have, look a little bit at some open path technologies, and then we'll work our way up to doing some of this in real time and moving with the PTR mobile platform. And then we'll kind of throw it all together with the software that we use to start this. And I messed up my clock timing here, so if I go long, Steve, please let me know. So before we start any kind of monitoring, we really need to sit down and determine exactly what we need to do and what needs to be accomplished and how we're going to go about doing this. So a lot of times you'll come up with a general monitoring plan here, what you're going to look for, how you're going to do it. What kind of quality and documentation do you need? Is this going to be legally defensible data? Is this just for engineering purposes? So we'll work with the general contractors who are going through this. We'll talk with the operators, the companies, and sit down and develop anything that needs to be done, and we'll get that ready. So these are a few examples of some of the different systems we're currently using for fence line and spot monitoring. The nice thing about these systems is they're very user-friendly. They're easy to deploy. They can be equipped with a variety of different kinds of sensors, depending on what you're looking for. And if we deploy them with the MET station, which we do in a lot of them, you can actually use some of this data for dispersion and windrows calculation. The really great thing about these, most of these systems are self-contained. They have their own battery system, and most of them have a solar recharging panel and a 4G cell card in them so that they can communicate back and forth with like a central data station. Clients can log into, look at their own data. If we have an alarm system, we'll set an alarm and the software will automatically call us and the client, whoever needs to be notified, so that we can take the next appropriate step. So these are nice. We deploy these. We kind of set them and forget them type situation, and a lot of these have been in use for a long time. Doesn't do us a lot of good if we want to cover a lot of area. So if we want to look at a lot of area, then we're going to look at something like an open path fence line system. Now, the previous ones were stationary. So here we can take this system, deploy it out, and we can look at path lengths of up to almost 1 kilometer. And we set these up in a variety of different ways, but usually we set them up with one light source, and then we have various retro reflectors deployed in this demonstration here. You've got, oops, hang on a second, that didn't work. You've got your light source here, and it coming across in a reflector, so you're going back and forth. So anything that goes across this path system is detected by this one is the FTIR. To save space, if the wind's blowing this way and you have another system set up, would be a UV DOAS system where same basic kind of setup with a reflector and a light source, a little bit different detection system there. You're looking at optical absorbance there. So now this is kind of what you're looking for when you set these out. You want to make sure that you set these across where you're going to be predominantly downwind of what you think is the source. So here you're coming across the plume, and in this particular case, there's 3 little point samplers that are in place as well. If you try to correlate them, let's talk a little bit about some of the shortcomings of this system. If you're going to try and correlate this open path data with these point source samplers, you're going to have a hard time doing that. This is not going to see the full extent of the beam that this one is, and this one is going to see less than this one. So really the only way you can accurately represent what's going on is to use a lot more reflectors and have a lot more paths. So right now, really this is kind of just an alarm system. Let me get back over here. We use this, and this works similar to you can trip alarm and you can do some measurements here. The real big issue, though, is how do you validate this? How do you know what you have and what you're reading is actually true? And that's difficult to do. And we found that the more paths you have, the more accurate your system becomes. Now, this is some pictures of actually deploying the system out in the field. If you look at the top left picture, you can see the IR source and the reflectors with all the orange lines in the back. And this is a typical deployment of this. You know, you set it out, you have multiple reflectors coming back. This is what we call it little taco truck. This is where the actual source sits, and you can see the pass-throughs on the vehicle. So it aims through here, it hits however many retros it can hit on this side, and then it turns automatically over to this side, and then you'll pick up reflectors that are deployed that way. Here's some of the guys actually installing the retros. And this is just an example of an actual test that was done at a refinery loading dock. You can see, I'm sorry for the picture quality, it's a little bit hard to see, I know, but the source is here, the IR source is here, and you have a path that goes straight up here, and then you have one that kind of angles out to the left. So if you look at this, you can see all these green dots, and these are actually hits for ethanol. This was a loading rack where they brought in ethanol to mix into the actual gasoline system. So we did trace back by using some of the algorithm software and a lot of the data points. We did trace back to, and you can kind of see in this picture, there's the trucks there. These were actually when they unloaded the hoses and took the hoses out of the vehicle and had them open is when we saw the biggest spikes in the data. So we have these sensors, and now it's great. We see all these measurements, and we have the open path system, and we get a lot of measurements from that, but we have to do something with this. So we want to either employ multiple sensors to get a lot of data, or an open path system with a lot of retros to get data back to put into our triangulation software to actually figure out where this leak is coming from. And you can also determine the extent and concentration of the plume if you can capture the entire width and do some flux and dispersion modeling as well. So this is kind of a little bit maybe easier view to see, where you have your source and you have different retros placed along a certain path, and you're going to aim and get a short path here, and you're going to have a path here and another set of readings. So you've got multiple readings you're going to get from multiple locations. And this is one that's actually out in the field now. You can see here, this is the source. You can see the different retros that were set up in different sampling locations. And if you put this into the software that we have, and I'll show you that next, you can see that this is the highest probability area where this emission is actually coming from. This is another example, and this shows stationary sensors and a MET station, and we wanted to determine where the emissions are coming from here. You can see the 6 sensors. You've got 1, 2, 3, 4, 5 here, and then 1 back here as well. So you have the 6 sensors deployed. And if you look at the small graph over here, this is the geometric array calculations that the software uses to determine the location. So the more data narrows the location probability, and this area keeps getting smaller and smaller with more and more data. So you're narrowing your area, and you're increasing your probability of it actually being detected. And that's what you see in this spot here. So it's great. We can do this on stationary, with stationary sensors and open path. But what if you want to move this around? If you don't want to deploy all these sensors and spend all this time, the next logical step is to take this mobile and do it on the fly. And that's where this comes in. So switch over a little bit now and talk a little bit about proton transfer reaction, time of flight mass spectrometry, which is a big mouthful. So we usually just abbreviate it PTR. So in the top left up here, this is our mobile testing platform. This is one sampling boom in this system up here. So at the very top is the meteorological station and the GPS receiver head, and then you can introduce sample this way. Also at the top, it's kind of hard to see in this picture, I apologize, but there's a boom here that can also be deployed out in front of the vehicle, and we can sample actually in front of us if we think there's something that's going to be interfering behind us. So we will deploy this out. This poor guy will sit in the back, and this guy will drive it, who is Art. This is the driver view back, so you can kind of see me stuck back here in my little cage running the instrument while we're actually moving, not down the road. We don't do this at high speed, but we do this when we're doing our grid mapping. So what is PTR? It's kind of a fancy mouthful of terms. But it's really the nuts and bolts of what we're doing here. So in the mobile platform, of course, we have the PTR itself, which is this little unit down at the bottom. It's about the size of a dorm room fridge, really. Weighs a heck of a lot more, but it's about 500 pounds, but it is fairly small and robust. And then also in this vehicle, we have a rack system that we can deploy regular FTIRs, optically enhanced FTIRs, TDL systems, cavity ring downs, whatever we want to put in the rack system, depending on what we're looking at. So this is kind of a nice little schematic or a little animation of what's going on in the PTR and what makes this really happen. So here we're going to talk about these reagent gases in a minute. So we have water, oxygen, and NOx. So here, water is going to come up into this little hollow cathode ray, and it's going to generate hydronium ions. These hydronium ions are going to react with, wait for one to pop by here, a little VOC molecule will come up here and will interact with these in the drift chamber. They will be accelerated down this chamber to the mass detectors, and then we end up with a series of signals that kind of look like this here on the bottom. And I'll go over this in a little bit more detail, of course. So how do we actually generate, because everything is an ion here, so we have to generate some ions. So we have 3 different modes of reaction that we can run this PTR in. The most predominant and the one that's used probably 95% of the time is the proton transfer mode. That was what the little drawing showed. You take a water molecule, you attach a hydrogen ion to it. allow that to react with whatever your target molecule is, transfer that proton over, and now you have a charged source that has a atomic mass of 1 more than the parent molecule, and it's charged. Another mode is an association mode, which I'll talk a little bit about later. And then the final mode is charge transfer, where you take a particular gas, in this case it's oxygen, you ionize it, and then you take that ionized species, react it in the drift tube, and it just charges this now to a positive charge, and the mass stays the same. So these are the 3 that we use. The great thing about this is we can switch back and forth between these modes in a matter of a minute. And which reagent we use depends on which compound we're looking for. And I'll show you how we determine that here real quick. So this is kind of our PTR guidance Bible. In order to be able to use it, we have to make sure that the molecule of interest that analyte we're looking for will react with the species we generated on that last slide. So, and these are all based on proton affinity. So we are looking for a molecule that has a proton affinity. It has to be higher than our reagent generated gas. So let's say we're interested in BTEX. So if you look on here, if you find benzene, there's benzene and toluene, and the other ones are up here. These are all above the hydronium line. So hydronium would be an acceptable reagent gas to use. It'll transfer its charge to toluene and benzene. You can go ahead and do your analysis. Now, if you're looking to do HRVOCs, which I'll talk about a little bit later, you will see that you have ethylene and stuff down here, which is below the the hydronium line. So now we're going to be forced to switch and use either NO or oxygen to generate those ions. If we use the hydronium, you won't see them, period. So that governs what we're going to use and how we're going to go about generating these ions. So you have to know a little bit about you have to know a lot about what you're looking for and how you're going to go about generating the ions that you need. So now we've got the basics down. We're going to generate some ions and we're going to do some analysis. So let's look at everyone's favorite, which is now ethylene oxide. So a huge environmental issue now and going forward for the foreseeable future. Several problems with this compounds in terms of analysis methodology. If you'll notice, they're both the same molecular weight, both 44.05. So if you just do a straight electron impact mass spec, which is your lowest detector, you're going to see 1 peak. The other issues, and we found this looking over some older data and doing some tests ourselves, that acetaldehyde has been characterized as ethylene oxide in the past, so it's kind of been biasing your numbers high. You can separate this by GC, which I'll talk a little bit about next, but it's not easy to do. It's if you look at the boiling points, they're very low. You stick them in a column, they're very similar. So it's hard to separate these without especially columning. So I have spent a lot of time doing that work. We've come up with a couple of options to ensure and prove that we're only doing ethylene oxide. So how do we do that? One slide. So this is the I would call stack testing way to do this. This is a GC chromatogram up on the top. Have a mixture of acetaldehyde and ethylene oxide. Put them down a proprietary GC column, separate out the acetaldehyde and the ethylene oxide. This is an FID channel, so I know that I've got baseline separation here, so it's okay to go ahead and take these systems, since I know they're separate now, and I'm going to leave everything the same in the GC, the carrier pressure, temperature programs, pressures, but I'm going to take the output now, and instead of routing it to an FID detector, I'm going to route it to the PTR. I'm going to cut the concentration considerably because it'll swamp the system. So here I'm using hydronium, the hydronium mode. So we're going to transfer a proton over to the systems. And you can see as you do the injection, you've got your nice baseline, which corresponds to this area here. Your first peak comes out, it's acetaldehyde, come back down, have another peak that comes up, it's ethylene oxide, and you're back down to baseline. And you can keep doing this over and over with different concentrations, and basically you can generate a calibration curve by knowing what concentrations you are and taking the separate areas underneath. Take that out in the field and calibrate under those systems, and you're good to go in a stack testing mode. The problem with this is you can't really use this for ambient screening because you're looking at a 5-minute injection here and a little bit of re-equilibration time. So you're only going to get these about every, if you look on here, it's about every 8 minutes or so. So there is a time delay. It's not really real time. It is great if you're doing a method 18 compliance test. And we have done this, not using the PTR, but we have done it with other detector systems. And now we want to take this and apply it to ambient. In other words, we're going to do this continuous, but know that we're only looking at ethylene oxide. Hang on, excuse me. So here we kind of stepped back and looked at some base level chemistry in order to go on. We wanted to change this over. Instead of using hydronium like we did in the previous slide, we switched over to oxygen mode. And the reason we did that is we found that if you generate the oxygen ions here, which is this dioxygenyl, which is the O2+, and it has this 32 mass, and we'll talk about that in a second. You also generate hydridodioxygen, which basically is protonated oxygen. So now you have an atomic mass of 33. If you allow this to react with ethylene oxide in the drift tube, you form this adduct or association product where the lone pair of the oxygen interacts with this one, and you have this stable ethylene oxide oxygen complex and the hydridooxygen complex that we can actually see in a detector. So we can see this. So if you take your 44, add the 32 and the 33, if you monitor at 76 and 77 atomic mass units, you will see that peak corresponding to ethylene oxide. So that sounds good, but we need to make sure and we need to prove that we're actually only seeing ethylene oxide here and not both. So in order to do this, we set up a couple of experiments to confirm what we're looking at. We had separate calibration cylinders of acetaldehyde and ethylene oxide, and we set the PTR operating conditions up for the oxygen mode, and we did the first analysis. So you see here, this is just a nitrogen baseline. This is monitoring mass 75, by the way. You see the baseline here, nothing, nice stable. We introduced 2 ppm of acetaldehyde only, and you see a nice no response here at the 75 or 76 one as well. I got a little detail on that too. And then if you move along and inject 2 ppm of ethylene oxide, you get this really nice response out of the system. So that's what this looks like over here. This is actually some of the software that runs the actual spectrometer. And you can see here, if you monitor this mass, I'm going to go to the blow up here. So this is that other side expanded. So same experiment. If you look at this mass, this is 44. So the oxygen does react with the acetaldehyde. It transfers the charge over. So you have now a mass of 44 with a positive charge, which is what you see on these red lines. So this is the base, then you have 1 ppm, and then you have 2. If you look at the green line, and I'm sorry the picture's out of focus, when I expanded it, it wouldn't blow up any much clearer, but if you look at this line on the bottom here, this is mass 75 and 76, and you see that when you're shooting the acetaldehydes, you get no response out of this in the bottom. So that confirms that we're actually only seeing ethylene oxide and not the mixture of the two. So we're very happy with this. This now allows us to do real-time ethylene oxide mapping and plume detection with the instrument. So of course, we always want to get out and see how this works in the real world. So we took off and did a little road trip where we're monitoring ethylene oxide while we're actually driving. And this is to the airport around here in Chicago. I won't say the name. We'll come back to the airports a little bit later too. But so this is what. I can't do that with the cursor. Shoot. Excuse me. I can't be on the cursor to make this work. Oops. There we go. So this is a real-time plot of ethylene oxide as we are driving. This is on the north side of Chicago. And these are the detection, these are the concentration hits. We're going at 65, 70 miles an hour. And then we ended up going down by the airport to do a little monitoring there as well. And you can see the ethylene oxide map around the airport. Now I cut this data amounts down because this is one of the first times we were through it. So it's a little choppy, but you can see it shows considerable ethylene oxide around the airport. And we'd expect that. This particular area here is a very large interchange, and this is, I can't remember exactly what this one was, but I believe there was a lot of construction equipment here, so we saw a big spike out of that as well. So what are we really looking at when I'm talking about this is the signals that we get? This is the actual output of the PTR analyzers, and this we're looking at the mass to charge ratio, which really is the time of flight. In other words, how long it takes from when we generate that ion in the drift tube until it hits the detector. That time corresponds to a mass or an M over Z number, and then we use those M over Z numbers to determine what's there. And if you look at this, when I first started doing this, I thought, wow, this is a mess. I don't really even know what I'm looking at here. And I do kind of understand a little better now, and they said you would as you go along. But so you see there's obviously something here around 200, some out here at 330. There may be stuff here around 107, 93, 79. So it's very difficult to work with this, and we prefer to work with it in this mode. So this is what we're really looking at here. This is those peaks that we saw earlier. This is the linear representation of those now instead of the logarithmic. And you can see that our mass here at 79 corresponds to benzene, 93 is toluene, and then the peak over here around 107 is the xylene and ethylbenzene compounds. So each raw peak represents an area. There's an area underneath these peaks, and we can use those areas under the peaks to determine a concentration. What really threw me the first when I saw this spectra was I couldn't for the life of me figure out what mass 85 and 105 were, because I was shooting a calibration gas cylinder that only had BTEX in it. So after a lot of head scratching and gnashing of teeth, I actually realized that it's contamination. And my learned lesson of the day or week was that you don't shoot thiophene or styrene through your environic systems, no matter how dilute they are. So that's actually what these are from. These are from previous experiment calibration gases. So you can kind of ignore those. That's not what we're looking at here. But so let's go back and take these ion counts now that we're looking at and actually do something with it. So this is we call these our stair-step calibrations. These are the direct interface continuous calibrations for BTEX in this situation here. You can see the benzene, toluene, xylene annotations off on the right. So this is the output at different concentrations. They should look familiar to a lot of you who have done stack testing, because they're very similar plots that you would see if you had a hydrocarbon analyzer or a NOx analyzer and you plotted those out as well. So here with the funnel off mode, which I'll talk about briefly, this is the different concentrations, so you can see the responses on the side. This is about 25 parts per billion here. when we decide we really need to look low and really want to push our detection limits, then we turn the funnel mode on, which is the PTR in turbo, basically. It's much more intense focusing of the ion path, so you get a lot more, you're really brightly focusing. Now, you do get a little bit more noise here, but this is 100 parts per trillion, 50 and 25 ppt that were generated. So great response when you would turn the mode on. The only problem with using the funnel, if you get a spike that's 50 parts per billion, you're going to saturate the system. So it's fairly rare that we use the funnel on in any kind of continuous modes. Most of the time it's in direct mode. So we're going to take all these data that we generated here on the stereostats. We're going to average these responses for each one. And we're going to use those to generate a whole bunch of calibration curves. And I have hundreds of these for different compounds and different reaction conditions. And so the main thing really here to take away is that these analytes and the responses that you get out of the PTR are very linear. And these are 5-point calibration curves from 5 parts per billion up to 100. So you can see now we have the equations for each line here, and each one of these says 80 Townsend, 120, 150. Those are different operating conditions for the drift tube and the reaction chambers. So different conditions give you different coefficients and slopes. So that's why we have so many different ones at different modes of operation. So that's great. We have all this. We take these equations, we put them back into the actual PTR software, and we use those to generate documented traceable ambient calibration curves. So now we're ready to take this out in the field and do this, and I actually do these when I'm in the field as well too, but take these and use this to generate traceable ambient data. So after we got this, we decided we'd do a little trip with BTEX back to our airports again. And we had done a test previously in February of last year. And this was in April when we wanted to come back and revisit this. And of course, that's right during the really tough phase of lockdown for the Illinois COVID response. So how are we going to do this? So we're going to get our van together, pack everything up, find a couple of dummies who will go out in the middle of a pandemic and do a little bit of testing here. So we followed all these steps. We pop on. This is the major east-west interstate in Illinois to O'Hare, and this is about 10:15 on a Monday morning, and usually it's bumper to bumper traffic, and no, you're going 10 miles an hour. This is it. As you can see, there is really no one there. It was actually kind of almost eerie, but really very strange. In the 25 years I've lived here, I've never seen this before. And then we're actually driving down here, and I can actually control the instrument from inside the cab as well, so I don't get bounced around in the back. So what are we going to come up with? So this first graph represents the testing we did for BTEX prior to the lockdown in place, and you can see it ranges anywhere from a little bit below 3 to above 3, and you have some spikes going around. And the bottom line, the blue is toluene, the bright green is ethylbenzene. So you can see, we get quite a few spikes as we're driving along, and this is a little bit more graphical representation of it over here on this side. And I'll show you a couple of these later. But then during the lockdown, we wanted to see what effect this reduction in traffic really had on our roadway air quality. So this is that same testing across the same path again that we'd tested previously. And you can see a huge reduction in all of them, but specifically benzene. It's about 3.5 times lower than what we saw during normal rush hour conditions, which actually is a little concerning considering I drive in it every day. So, but we were quite happy with this, and I wanted to see, and this is kind of a more visual plot, just to give you an idea of what this actually looks like when we're It's supposed to be, there we go. This is the same map. Now this is a BTEX continuous map, and you'll see here that these peaks are a little bit, there's a little bit more data here than what we looked at with the ethylene oxide. So now you're winding in from our office up here in the northwest suburbs. We're going around, we're actually in the terminal area down beneath, and we're monitoring for these things. And then we drove out another different direction. We couldn't go back the same way. So you can see visually what's going on here. And it's actually really interesting. If you step back and look at it, you saw those peaks on the previous data, but when you actually go back and put them against their geographic location, it tells you a wealth of information. So this one in particular here, this is the huge hit of xylenes that we saw. And actually there is a huge, you can't see it's on the other side of the road, but on the other side of the graph, but there is a huge road construction project going on, and there were tons of semis full of asphalt and bulldozers and stuff. So the background levels of xylene and toluene there were just really, really high, and that's what we're seeing here. So now it was a lot of information, and one of the great things about plotting this way is we can cut it into smaller pieces, and we wanted to take another trip, and actually Pete Zemek did this drive here, and this was from the 4C conference in Austin last year back to our office in the Houston area. So Pete did the same thing, drove over, had the instrument running while we were in motion, and mapped some of the concentrations along the way. So I mean, this is a lot of data. So it's kind of cool to look at this way, but if you really want to start making some sense of it, then you need to break it into some smaller pieces. And here you can see the individual peaks. I think it's about 65 feet between each measurement, going down the road at around 60 miles an hour. So here, peak was coming in, this is going down 610. And if you notice here, these are huge hits of xylene right here, and then a little bit more over here, down here. So we're trying to figure out, what would be causing that. So, we rotated around and looked at it again over here, and the wind predominantly at this time was going in this direction. So this was coming from over here. And if you do a little research, these are some reclaimed areas in the San Jacinto area that were previous, the previous sites that are no longer in business. So these are remediated sites, but there's still some xylene issues coming off of that. So now, if we really wanted to pinpoint exactly where this were coming from, we wouldn't be doing it 65 miles an hour down the highway. We'd stop and we'd set up a grid pattern, and we would chase a plume basically until we found it. We'd sit there and monitor and accumulate data, just like we did with the stationary sensors, to build into the model for the triangulation. This is just the last view. So this is from Houston here, clear back over to Austin, way over here. But it's kind of interesting when you look around and see, and it's kind of a little bit different to think about. So now, of course, never being satisfied with enough, we had another conference out in Denver. So my friend Cody drove the PTR van back, and of course I wanted to monitor along the way. So this is a 2-day trip that I kind of summarized here in a little bit of data. So we're going across Nebraska now. We end up here coming across 80, going into Iowa. Now we're over by Iowa City. And this took place this was a 2-day drive for Cody. So, and I'll show you what these high little peaks are here in just a second when it finishes here. But if you look at this set here, this is a huge interchange and truck stop. And here, this is the largest truck stop in the United States. This is the I-80 truck plaza. That's in Iowa there. So you would expect high emissions there, and you did indeed see them. So now I'm going to switch gears a little bit here and talk a little bit about HRVOCs and some of the OHAP analysis that we've done. So HRVOCs are either ethylene and propylene in these areas, or ethylene, propylene, 1,3-butadiene, and the 4-butene isomers in Harris County. And these are common in refining situations in specialty chemical plants. So our goal here, one of the group goals, was to come up with a method to do these using the PTR, because the laboratory analysis on these are hard. The detection limits are very low for the compliance levels, and we would like to be able to do this in real time, actually monitoring along fence lines and situations like that. So a little bit of work that we had to do to come up with this. We came up with a couple of really good viable alternatives here. So now one of the key issues of this is that if you remember back to the big dotted chart, we have to do this analysis with oxygen because you can't see ethylene and propylene with hydronium. One of the issues with oxygen is not quite as sensitive. The reaction kinetics aren't as favorable as water, so your response is a little bit lower. So it took quite a considerable amount of time to come up with PTR operating conditions that allowed us to do an HRVOC analysis and see all the components at a really low level. So if you see the, oops, sorry, go back to this. If you look at the bottom here, these are the traces. This is the ethylene response. This kind of bright green line is propylene. The red line is 1,3-butadiene, and then this huge orange line is the butenes. And when I say the butenes, it's all 4 of them together because you can't separate them out because they're all the same mass. So it's the same issue we had again with ethylene oxide and acetaldehyde. You have the same mass. Now, and this is just some of the steps here where we do the calibrations the same way that we normally do. So I mean, we can see these, and that's not an issue. And normally HRVOCs are reported as total HRVOC. So it's a summation of all the compounds that are there. So in that case, it doesn't matter if you do butene separately or as a total, you're going to sum them all up and get a total number anyway. So we're confident now that we can see we can go out and we can do this direct path with, sorry, this pointer is just not behaving very well. No, I can't get it to go here. I'm sorry, I left my train. So you can see here we can do the butenes and the 1,3-butadiene quite low. We'll do the same thing here that we did previously. We'll use these to generate calibration slope and coefficients, and then we will put that into the software, and we can actually monitor with a calibrated traceable standard system and monitor for HRVOCs with the continuous interface. Situation does arise where we need to know the total of each HRVOC separately. So the only way we can do that again is to go back to the GC system. I'm starting to run a little bit late on time here, so I'll speed it up. So we can separate out the HRVOCs with the GC column system, take it out. Instead of running it through the FID, we can put it into the PTR. And that's what these represent here. I cut off ethylene here by mistake. It's propylene, the butenes individually, and 1,3-butadiene. 2 to 10 ppb by GC interface, 50 to 100 ppt by the direct interface mode. And this is actually what it looks like. This is a little bit blow up. So you actually come up with a PTR trace that is identical to the FID trace that you get in a normal system. So you have your trans, your 1, your isobutylene, and cis 2-butene, all separated out and quantified individually. So that's great, we can do that. So maybe we can use this for a method 18 type calibration and testing. So this is our first attempt at doing a method 18 test using the PTR. So we left the direct interface set up. I calibrated each component at 3 different concentrations, or maybe 4, I can't remember. And you come up with this calibration curve over here. I don't know if you can see that or not, I'm sorry. You come up with this calibration curve over here. And once again, we're very linear. Plethora of QA/QC requirements for method 18. You have a pre-calibration, post, challenge, and limit detection. So we passed everything except the post-calibrations on 1,3-butadiene, and that's because it was dragging off the column a little bit. So we changed column conditions. I didn't put the updated slide in, and we did come up with a system where this passes. So this was a laboratory test. Now, of course, we want to take it out in the field. Oops. Uh-oh. Did I lose the slides there?
Correct.
Yes.
Are they gone? Uh-oh.
They're gone.
Oh boy, that may not be good. Oops. There we go. Are they back now?
Yes.
Okay. Sorry about that. So we wanted to take this out into the field. We did it in the laboratory, and we could do the pass the QA/QC. So this is an actual field test that was performed in Ottawa, Iowa, and one of our clients' sites. They allowed me to come out and do this while we were doing some other testing. And we performed a full method 18 with 1,3-butadiene, styrene, and acrylonitrile. I'll just show you a couple of them real quick since we're getting low. Field calibration, same as method 18 if you were doing direct interface. Did the recovery biasing tests, which have to be between 70 to 130, which you can see down here. Easily passed that. This is what it actually looked like out in the field for each injection through the GC, and this is 500 ppb, 250, 125, and 50, clear down here. Generate the calibration curve. It's got a great R-squared value. We're ready to go. Did the sampling. Oops. And this is the acrylonitrile one, same exact thing for brevity of time. I'll just leave it at that. This is a little bit expanded view so you could actually see what we're seeing. We're looking at each individual component's mass, which 1,3-butadiene, acrylonitrine, and styrene. So you see them come through, you get a nice peak, you get a reproducible peak area-wise, so you can use this to perform a calibration. To go along with the rest of the method 18 requirements, we did do a detection limit determination. 2.4, about 3.7, respectively, parts per billion, and that's through 130 feet of 3/8-inch heated sample line. So I was really happy with that number. And then to finally prove that it's a valid sampling system and sample method, we can do a method 301 data validation, sampling validation. And that's what this is. And it's a pair of, it's 12 pairs of spiked and unspiked analysis. So you actually run some calibration gas up while you're sampling the actual stream. And that's what we had here. You can see down below each one of the 14 injections, all the data. It's a lot of numbers. It took almost all day to do this. And then you take those numbers, put them into our 301 statistical analysis sheet. And there are several criteria you have to meet here, and they met them all. But the big one is your recovery system valid? Is it with between 70 and 130 in order for it to pass the requirement? 1,3-butadiene was 110%, which is what this one is. Acrylonitrile was 105%, so passed that requirement. So it's definitely a valid sampling method to do this. This is what the actual tests look like. You can see we had to cut a hole in the bottom of the van to get a heated sample line in. So that's our entry point. It goes up, and you can see it goes clear up like 130 feet total. This is the GC system. This is the rack system that had the other analyzers in it. This is the picture for those in my company who don't think I go out in the field anymore, just to prove that I do every once in a while. And we ended up very happy with this. This turned out even better than I thought it would. We feel it's a valid way to do a method 18 type test, and we are actually working on another test method with the EPA right now to get this approved for use. So now I'm going to jump topics real quick because I know we're running out of time. So the whole point of emerging technologies here is to drive better and better detection systems and lower the detection limits for the analysis that we do out in the field. Current hot topic is acrolein, another one of these. Current methodology, if you do sampling in the field, if you do it by method 18, you're going to use GC. Maybe 1.4, 0.6 to 1.4. If you do it by conventional FTIR, 0.4 to 1 ppm detection limit. Sorry to go so fast, but we're running out of time. If you use optically enhanced FTIR, the StarBoost system is what we use, 35 to 90 parts per billion, which is a fantastic detection limit for that. If you take it one step further and push it to the PTR, get a detection limit around 27 to 50 parts per trillion, which is a weird number, I know, but I actually did it twice in the lab, and that's where these two numbers came from, 27 and 50. So very low detection limit. So what does that mean? What are we going to use this for? A huge issue, of course, is potential to emit in Section 112 of the Clean Air Act about major and minor source classifications. If you test on an FCC unit for acrolein, let's say, I averaged up the flows of 8 units that we had tested, got an average 12.8 million dry standard cubics per hour. So if you have a non-detect with the GC method 18 system, you put in 1.4 parts per million because that's your detection limit, and that comes out to be less than 11.5 tons a year. FTIR 8, StarBoost 0.7 tons per year now. And if you take it to the absolute limit right now, using the PTR, you're looking at 4.1 times 10 to the minus 4th tons a year. And same way with the typical heater system, 1.25 clear down to 4.5 times 10 to the minus 5th. So that is a huge potential reduction in emissions that you're reporting. So this is a significant leap forward. It can make a really big difference going from a minor to minor source if you have multiple units in a facility. And then I do want to throw a couple more slides here just at the end. This is work that Pete is working on right now. This is another hot topic, which is the PFAS area. And it's really driving, type of work is really driving the need for real-time PFAS analysis out in the field. And currently, samples are collected using some kind of absorbent media, high volume, long sampling time, and then you send these samples off to a laboratory after you're done with the test program, and you get your results a couple weeks later, and you kind of hope that you passed. So it'd really be nice if you had a way to be able to see if you have any PFAS present in your systems. Now, currently there is some work that we've heard rumor of with an 80-meter path length IR system. This is work that Pete has come up with a 5.11 meter conventional FTIR system that we have tons of. So the top spectra is perfluoropentanoic acid. Now you know why we use all these letters instead of saying all this stuff. And then the bottom one is the perfluorobutane sulfonic acid. These are two really big ones. This one because it has the sulfate group in it as well. This is the acid group on the end. And these are two other ones that he's worked on. This is Pete here, for those of you who don't know him. This is all his stuff. He came up with it. It's great. So a couple more that he did. And here is the region of interest that we're looking at to actually do the quantifications for these. I think his next step is to generate some of these compounds, using a certified calibration device to come up with some standards and generate some LRF calibration files for the fleet of FTIRs that we have in the company. And we are also working on, this PFAS analysis for by PTR as well, so we can get a much lower detection limit. So congratulations to Pete for pulling this off with a 5.1 meter instrument. And I do have one more thing, if you have just a minute, which a lot of people have asked what our triangulation software really does. You know, we keep talking about it, but what does it really does? And this is a kind of a representation of some work that we did testing the system. We have some client work, but it's kind of hard. When you see an aerial view of a lot of places, you can tell what facility is. So to avoid that, we did a demo in an actual large space. So this is a graphic representation of what our software does. So we created a source of emissions of acetone, and then we put it out, and we took the PTR, and we're going to find this. So any conventional search system, you know, it's they call it mowing the grass or walking the grid, but basically that's what you do here. And you can see we started back here in the corner, and you walk up and down, and we got some hits here, which is bigger concentrations. Come back down, some more hits in this area, and so on and so forth. And this is a long video, so I apologize for that, but oops, I do have to get this off to get it to move forward. So this keeps going on, and this goes on and on and on, so I'll jump forward since we're running out of time. So as you can see, this is really fast now as we're walking along. And you can see you get more and more as you go in. So we've done a grid system, and that allowed us to you know, find out where the plume is. So now we're going to go back, and we're going to sit in this plume for a while, and I'm looking for a particular time slot. There we go. So now we've got all this data. So now we're going to make this pattern. We're going to find out where it is. We're going to coalesce. We're going to shrink this down, our circle of probability, until we actually locate the source. And this is what we do along fence lines and in process units looking for leaks. We find the plume, we sit and monitor it. And as we're monitoring, the software is calculating the probability of the location, and it's getting tighter and tighter. This goes on, sorry. It's not the fastest video in the world in here, but so now we're getting smaller and smaller, and eventually we're going to get to the point where we're not changing the size. We're not making it any smaller. We're just repeating it over and over. So that gives us our location peak, and that's this orange circle here. So that's the calculated spot. It's about 8 or 9 feet wide. The source was actually right at the end of this white line, and it was about 6 feet away. So we were very happy with that. So I was expecting 15 to 20 feet, and we came back that tight. So we were very happy with that. So we use this out in the field to find some leaks and do a little bit of monitoring and help out if you have some blown suma cans on a fence line, or some method, some benzene tubes that are out. We can take this system in, usually within a day or two of fence line mapping, depending on how big the facility is. We can plot out where most of the leaks are and where most of the sources of those are. So with that, I will take your questions. I thank you for listening, and I'll leave this up so that you have our emails if you have any questions later. And I'll try and get back to the camera system. So.
Okay, there are a few questions. Can you use bloodhound? Yeah.
I'm sorry, Steve, I didn't get that.
Can you use bloodhound FTIR?
Yes. Anything that gives you a concentration and a location, as long as you have the meteorological data and the GPS weather station data, wind direction and all that, and the concentration, yes, you can use it to triangulate back to a probable source.
What is the cost of this type of MS instrument?
I'm sorry?
What is the cost for this type of instrument?
For the PTR, I believe it was 600,000 for the instrument alone. And the entire setup ends up in the very high 6 to low 7 figures to get everything outfitted and equipped the way that we have it. It's not a cheap mode.
That's correct, Steve. Yeah, we can build a van for about 800,000 fully equipped.
Okay.
Does Montrose have any experience with ethylene oxide leaking into heat exchange systems, cooling towers, and any test methods that can be used to detect EO to cooling tower?
Yeah, the way that you usually test for that would be you have a couple different ways you could do it. You could use the El Paso stripping board, which is what's used for HRVOC testing. You actually pull the cooling tower water into it's about a 2.5, 3-inch round column packed with zeolite saddles, and then you run a clean airstream, bubble it up through that, and it strips out the species that are dissolved in the gas, and then you collect that gas in a Tedlar bag or another kind of container, and then you send it off for analysis. Or another way you can do it is you can also take a full vial sample with no headspace, seal it, and send it to our sister lab, Enthalpy, and they will do a stripping and collecting purge and trap GC test on it, where they will take that water, put it in a system, bubble it, collect everything on an absorption trap, and then desorb it and flash it to an instrument to determine the quantity.
Do you assume 100% efficiency of the ionization, and can that be demonstrated?
Which ionization?
I am not sure. Thomas, if you would like to add some clarity on that question, because I'm not sure what that question means.
Yeah, in the proton transfer instrument.
No, it's not. It's not, and we account for that by monitoring and doing using what's called a corrected count area. It is not 100% efficient, and either the generation or the transfer, either one, is not 100% efficient. And we have a series of equations that we can use to calculate the concentration using those. They're K factors, is what they're called. And each compound has its own unique one, and then the equation is about this whole page. It's a very large equation that you can use to calculate an approximate analyte concentration using the corrected ion counts, the ion efficiency, the Townsend value. There's a ton of different variables. We will do that on a screening basis if we are somewhere and we are screening for a whole plethora of compounds. We can give, and it's usually within 10 to 20% of the true value. And in the part per billion range, that's really not a whole lot of variance. If we are going to do a source test or some highly accurate fence line monitoring or concentration monitors, we will generate the cal curves and take that into account. So that's factored out and traceable.
Yeah. So Tommy, if we run it empirically and we do our spike recoveries, all of those errors or sources of inefficiencies in ionization they drop out.
Okay, thank you.
Okay, Stephen, thank you, and Peter, thank you. Thank you to all the folks at Montrose. And thank you for everyone who attended today. And with that, we will conclude the webinar today. And again, this webinar will be available on YouTube on the 4C website. And we look forward to seeing you all in August 18th to the 20th, Austin, Texas. Thank you very much. Have a great day and be safe.
Thank you.